I want to take a look at an integral here that I should probably be able to do in my sleep here. In fact, I will do it using the fundamental theorem of calculus at the end to check my answer. But I want to approximate it here using Simpson's rule. This will actually lead into the next video where we look at error approximations and getting a good idea of how close our approximations are. So anyway, I'm going to do Simpson's rule, and I'm going to go way out on the limb here and say, let's do it with n equals, how about 2? So delta x is 8 minus 2 over 2. So that would be 6 over 2. So delta x is 3. So that interval from 2 to 8 is cut up into 2 equal pieces. Delta x is 3, so from 2 I move over here to 5, and then 3 more gets me 8. So 2, 5, and 8 are the x values I'm plugging in. So Simpson's rule says this integral is approximately equal to 1/3 times delta x here is 3, times, take the 2 and plug it into the function. This is my function right here. So I've got 2 cubed minus 2 times 2, plus 4 times, take the 5 and plug it in. So 5 cubed minus 2 times 5. Actually, remember Simpson's rule. The coefficients that we use are 1, 4, 2, 4, and so on. The last one we're going to use is 4 before we finally end up with a 1, right? So 1, 4, 2, 4. So that was the 1 times this one, 4 times that one. And the thing is, I'm at the last one now because I only have 3. So I'm using a 1, a 4, and a 1 to multiply there. So this is plus 1 times, plug the 8 in, 8 cubed minus 2 times 8. And so then I'm going to calculate this. Well, this is just a 1 there. And this is 8 minus 4, that's 4, plus 4 times 125 minus 10, so that's 115, plus, well, 8 cubed is 512, minus 16 is 496, for a grand total of 4 plus 4 times 115 plus 496. And I get, or my calculator gets, 960. 960. Well, that's my estimate of this integral, right? Integral of this cubic with n equals 2. Let's see how well we did. Let's actually do the integral, because I can integrate from 2 to 8 of x cubed minus 2x dx by just using the antiderivative here in the fundamental theorem of calculus. So I've got x to the 4 over 4 minus x squared evaluated between 2 and 8. So that's 8 to the 4th over 4 minus 8 squared minus what you get when you plug a 2 in. So 2 to the 4th over 4 minus 2 squared. And that ends up equaling, stuff in the first parentheses here is 960 minus the stuff in here ends up being 0. So I get 960. How's that compare to my estimate? Oh, exact. Coincidence? I don't think so. It turns out that there's a very close relationship between cubic functions and quadratic functions. In the same way that I can approximate, if I had an area that I was trying to figure out that had a straight line but not flat, so a slanted flat top. If I'm looking at trying to figure out that area, I can actually essentially use the midpoint approximation here, take the point in the middle and draw a horizontal line and say the area underneath that horizontal line is the same as the area underneath the slanted line. Right? Because this stuff and that are the same. Anyway, cubics, I'm trying to do a cubic here, and I said I'm going to take the starting point, the middle point, and the end point, and put a quadratic function through there. So somehow there's a quadratic that goes through there. And it turns out, although my picture doesn't really recognize that right here, but there's going to be some of the cubic that's underneath the quadratic, and there's going to be some of the cubic that's over the quadratic. And apparently those two things cancel each other out, because it turns out if you're using Simpson's rule to approximate a cubic, you will get it right every time. And we'll see why when we do the error estimation in the next video.